Video 4 gets into the motor principle. The very first thing they talk about is the fact that when you have current carrying wires close together, their magnetic fields will interact with one another. If you haven't watched video 4, the motor principle, I highly suggest that you go back and watch that. The simulations and the animations that they show you are really great for understanding how these fields interact with one another. The first thing we're going to do is look at what happens when you have current flowing in the same direction. So when current flows in the same direction in both of the wires, those wires will attract to one another. That's something really important to know. So what I'm going to do is draw diagrams that help you analyze this. I'm actually going to draw a cross-section of wire. So instead of drawing the wire kind of laying horizontally, I'm going to draw a cross section. So instead of the wire being horizontal, where we look at the flow of electrons either going left or right, I'm going to draw a cross section. So it's like I take the wire and orient it like this. And now electrons are going to flow either down my pen away from me into the paper or up the pen out of the paper towards you. So first let's have electrons flow away from us. So again, if I'm looking at my wire like this, electrons are going to go away from me. So from the tip or the back of the pen really down to the tip, right? So this will be represented by an X. I'm going to have another wire close to it where current is flowing in the same direction. So what I want to do now is analyze the magnetic field around both of these. So I'm going to use left-hand rule number 1 since they're straight wires. So that means I'm going to use my left hand. My thumb is going to go in the direction of the current, which is away from me, so into the paper. And then my fingers are going to curl around to show me the magnetic field. So you can see here my fingers are curling in a counterclockwise direction. So I get this circular magnetic field around that wire. Arrows indicate it's going in a clockwise direction. So I'm going to do the same thing for wire number 2 here. My current is going into the page, so thumb goes in, and my fingers are going to curl in the same direction here, counterclockwise. So I have another circular magnetic field, and I have arrows to indicate that counterclockwise direction. Now, to determine how they will interact, we want to look at what happens between the wires, so in this area. So the wire on the left has a magnetic field that's going in the upward direction at this point. The wire on the right has a magnetic field that's going in the downward direction. So since these are opposite, we know that opposites attract. So those two wires will come together. I could look at something very similar with current flowing in the other direction. So if I have now a cross section of wire where current is flowing out towards me, right? So again, I'm using my pen in this orientation. So current is now going from the page up towards my face. Right? And I'm going to have another wire with that as well. And then using left-hand rule number 1 again, my thumb goes in the direction of current, and that dot indicates it's coming out towards my face. And then my fingers are going to curl now in a clockwise direction. So I have this clockwise direction, and I'll get the same thing around the second wire because the current is flowing in the same direction. And if I analyze the area between them, you can see that these will attract because they point in opposite direction. Okay. When you have current that flows in opposite directions, something else will happen. So this was when current was in the same direction. If you have current flowing in opposite directions, so current flows in the opposite direction, then your wires will repel. So going back up here, this should say current flows in the same direction. But current flowing in opposite direction. So I have 2 wires, and let's have this current go into the page, and I want opposite direction here, so I'm going to have current come out of the page. So I'm going to use left-hand rule 1 to draw my magnetic fields. So into the page for the wire on the left there, current goes in, so my thumb goes into the paper, and then my fingers curl in a counterclockwise direction. And then wire number 2, thumb goes out of the page because current's coming out of the page, and I get this clockwise direction. So now you can see when we look at how those magnetic fields are going to interact, they point in the same direction. Right? And so when these are the same, or the way that we refer to it is like, right? We know that like things repel. So that's really what you're looking at when you are determining whether or not two wires will attract or kind of repel, move away from each other. You're looking at the magnetic field between them. You could do something very similar with bar magnets, right? So if I had two bar magnets that were set up, so this doesn't necessarily have to be current carrying wires. I could have two bar magnets, right? Let's put them in the opposite directions here. So north at the top for the one on the left, south at the top for the one on the right. If I draw the magnetic field, you know the magnetic field goes from the north to the south. So magnetic field lines go out of the north and into the south. Right? Magnetic field lines show you where your magnetic field is acting, right, in that direction. So my other one, I'm going to have out of the north into the south. So these will go in the opposite direction, out of the north into the south. So what you see here, when these are opposite, these will attract. Okay. If I do the same thing and I have them point in the same direction, so here you have north, south, right? North, south. You know, right off the bat, you know what happens when you put two magnets like this close together. Right? But here, this is showing you why that actually happens, because their magnetic fields are in the same direction, and we know that when things are in the same direction, or they're like, these will repel. Right? So you're analyzing the direction of those magnetic fields. So this is kind of its own, this doesn't have to do with current carrying wires, this is kind of its own little side note here. And you apply the same principles to bar magnets. Okay. The next thing that this video gets into is left-hand rule number 3, right? And really the motor principle. So the motor principle itself has to do with left-hand rule number 3. And this comes from Michael Faraday. So when we talk about the motor principle, you are looking at interacting magnetic fields. So the motor principle, you're placing a current carrying conductor in an outside magnetic field. Right? So this has to do with a current carrying conductor placed within, so let's just write this out, a current carrying conductor, right? So a wire that has electrons running through it, placed within a magnetic field So you're placing this wire in an outside or an external magnetic field, will experience a force. So it's going to experience a force that is perpendicular to the electron flow and to the external field, magnetic field. Okay. And this is where left-hand rule number 3 comes into play. In left-hand rule number 3, the key here is that your hand is flat, essentially, and your fingers are straight. Okay. In the first left-hand rules, the first 1 and 2, your fingers curled, but now your fingers need to stay straight. So before we even talk about left-hand rule number 3, let's kind of draw what's going on. So I'm going to place a current-carrying conductor in an external field. So I'm going to first draw my external field, just using let's just use bar magnets. Right. So you're only seeing part of the magnet. Let's have this be the north end of this magnet, and there's a south over here somewhere. And this will be the south part of this magnet, and north is over there somewhere. Okay. Now I'm going to place a loop of wire in this field. Now this is hard to draw, right? But what I'm going to do is place a loop of wire that looks something like this, right, in that field. Okay. Now I'm going to indicate the flow of electrons here. So let's have electrons flow this way through my wire. So electrons are going to go up through here, around this corner. They'll go in this direction. They'll go over through the loop this way and down. They'll come over here and out on that side. Okay. Now, the other thing to remember, when I have a current going through this wire, there's a magnetic field that gets generated around the wire. So you have these little circles around this wire, right, that represent the magnetic field here. And then you also have the magnetic field from the bar magnets itself. So there's a magnetic field here. I'm going to draw this. My diagram's going to get a bit messy. This field goes from the north pole of the magnet to the south pole, so it goes in this direction. So you see my magnetic field in this diagram is represented by these red or blue lines. So I have this magnetic field from the bar magnets, but I also have the magnetic field around the wire itself. And using left-hand rule number 3, we can see how those fields are going to interact. So in left-hand rule number 3, you have your thumb, and your thumb is going to be pointed in the direction of electron flow. Your fingers stay straight, and your fingers point, right? I'm going to write point instead of curl. Your fingers point in the direction of the external magnetic field. Right? So point in the direction means they go from north to south. So as a side note here, your fingertips point south, right, to the south, because that field goes from north to south. And then your palm indicates the direction of the force. On the wire. Or a particle, right? It could be a particle, whatever's in that external field. So I'm going to look at this side of my wire first. Okay? So my thumb goes in the direction, using your left hand, direction of electron flow, which is represented by that red arrow. So electrons are going up this way. Right? My fingers have to go in the direction of the external magnetic field, so from north to south. So my fingers tips have to point to the south. So I have to actually flip my whole hand this way. So thumb goes up in the direction of that current flow. My fingers point in the direction of the external field, so from north to south. And then my palm is going to show you the direction of the force. So it's coming out of the page. It's up towards your face. So this side of the wire is going to feel a force coming out of the page. So this is your force out of the page. So this part of the wire is going to come flipping up. Let's do this side of the wire. So on this side, my current is flowing down the page. Right? My fingertips have to go from north to south, and so now my palm is going into the paper. So this side of the wire, the force will be into the paper, or into your page. Oops, force is in, which means that part of the wire will be forced down. So what you have is that opposition. So this side of the wire is coming out, this side's going down, so it's going to end up twisting, right? And that's where you start to get this motor that is being represented, which is why it's called the motor principle. Right? So left-hand rule number 3 is a tricky one. We've applied it to wires here, but it also applies to particles. So you could have just one single electron that's being shot through an external field, which you'll see in some of the problems that we look at a little more advanced.